All right, welcome everyone. Today we're going to look at derivatives and parametric curves. So specifically, we're going to see how to calculate the first and second derivatives of y with respect to x. So we're going to see how to calculate the first derivative, dy dx, and we'll see how to calculate the second derivative of y with respect to x. And we're going to be doing this for a curve that's given with differentiable parametric equations. So we're going to see how to do this when we have a curve that's described using parametric equations. All right, so let's start with the first derivative. How do we calculate the first derivative? Well, we're going to be working with a parametric curve, so that means we're going to have parametric equations for x and y, and we just require that these are differentiable, so we can actually calculate their derivatives. And what we're going to do to calculate the first derivative, dy dx, is we're going to differentiate our y equation with respect to t and differentiate our x equation with respect to t, and then divide. So the y derivative goes on top, the x derivative goes on bottom. And that's so you can kind of see where this would come from. We have dy dx, so the y derivative's going on top, the x derivative's going on bottom. All right. With the extra condition here that the x derivative with respect to t does not equal 0. We don't want to divide by 0 here. It's undefined then. All right. So there is a lot of different derivatives here. And it can kind of get a little confusing when we have, dy dx, dy dt. What are we, there's a lot of, what are we doing here? So it's helpful to kind of keep track of all these different derivatives that we're doing. So when we write dy dx, what do we actually mean? So this is measuring the instantaneous rate of change of our y-coordinate with respect to our x-coordinate. So it's measuring how y is changing with respect to x. So this has to do really with the geometry of the curve. And we know what this measures. It measures the slope of the tangent line. So it measures the slope of the tangent line to the curve. So it really has to do with kind of the geometry. Now when we talk about these other derivatives, dy dt and dx dt, we want to think of these as these are time derivatives. So it's the derivative of y with respect to t. It's measuring how much our y-coordinate is changing over time. This is a velocity. We want to think of these two derivatives as velocities. So really these are measuring the change in x and change in y over time. So that's really what these different derivatives are doing. Dy dx, this is our kind of our classic one that we looked at back in Calc 1, where it really describes the geometry of our curve. It describes the slope of the tangent line. These other two derivatives, dy dt and dx dt, these really, we want to think of these as velocities. So with parametric equations and parametric curves, we want to think of, when we picture a parametric curve, we want to think of a particle that's moving in the plane. And so what dx dt and what dy dt are doing is dx dt is measuring how are the x values changing over time? What is our velocity in the x direction? And dy dt is measuring what is our velocity in the y direction. And so we have this formula here that describes, we can calculate dy dx as just the velocity in our y direction divided by the velocity in our x direction. All right, so this formula actually tells us a little bit more. It tells us how to differentiate. So if we had just some expression that we wanted to differentiate besides, say, y. Say we had some other type of parametric expression that we wanted to differentiate with respect to x. How would we do it? Well, we would take that expression, whatever it is, differentiate it with respect to time, and then divide that result by dx dt. So this is going to be helpful. So if we just had some expression that we wanted to, some kind of parametric expression that we wanted to differentiate with respect to x, what we would do is we would take that expression, differentiate it with respect to time, and then divide that by the x derivative with respect to time. And this is going to be useful for the second derivative. So keep this in mind with what we're going to talk about next, the second derivative. All right, so let's take a look at that. So same kind of setup here. We're going to have parametric equations for x and y. We want to calculate the second derivative. Now when we look at it here, we want to calculate the second derivative of y with respect to x. So how do we actually do that? Well, the way we calculate the second derivative of y with respect to x is we take our first derivative, dy dx, and we differentiate it with respect to x again. And this is where that little note about our first derivative comes in. So if we have something that we want to differentiate with respect to x, what do? We take that thing, differentiate it with respect to t, and then divide by dx dt. So in this case, we want to differentiate dy dx with respect to x. So we're going to take that dy dx and first differentiate it with respect to time. And then we're going to differentiate it and then we'll divide by the derivative of x with respect to t. So this is kind of where this formula is coming from. We know to calculate the second derivative with respect to x, we take the first derivative with respect to x and differentiate it again with respect to x. And by using that result, where if we want to, for our first derivative, anything that we want to differentiate with respect to x, we take it, differentiate it with respect to t, divide by dx dt. So that's precisely what we're doing here. And so there's a little bit of, this formula is a little bit surprising. So kind of, let's make this red. Warning. This might not be what you expect. So you probably want to think of, it's very tempting to say that the second derivative is just going to be the second derivative of y with respect to t divided by the second derivative of x with respect to t. And it's unfortunately not true. So this is not true. Well, actually, let's just cross out that equal sign. This is incorrect. So it's very tempting to say that the second derivative with respect to x is the second derivative of y with respect to t divided by the second derivative of x with respect to t. Fortunately, it's not. And really what's going on here, so we want to be careful with this. What's going on here is this is a chain rule. Really, this is kind of behind the scenes here, is there's a chain rule going on. So that's why this doesn't quite work out the way we would expect, is we actually have to use chain rule in some way. So really that's what's happening here. There's a chain rule. All right, so just like we would expect, though, when we talk about the second derivative of y with respect to x, we still want to think of this in terms of kind of the geometry of our curve. So this really describes, we use it to figure out where our curve is concave up and concave down. So it really describes the concavity of our curve. And it's going to be true here as well. So our second derivative, dy of y with respect to x, really has to do with the geometry. And again, there's this relationship here with these time derivatives. So we're looking at how our first derivative changes with respect to time divided by how x changes with respect to time. All right, so let's try some examples where we actually calculate these things. So let's look at example 1. We're going to calculate the first derivative, dy dx, where we're given parametric equations. So we have this parametric curve where we have x equal to t squared plus t, y equal to t cubed minus 3t, and we want to calculate dy dx. So we want to see how does y change as x changes. And so we're going to calculate dy dx. And we're going to use our formula. So it'll be the derivative of y with respect to time divided by the derivative of x with respect to time. So we're just going to go through, look at each of these equations, and differentiate with respect to t. And so when the variables kind of match, we're differentiating x with respect to t. Here our function is in terms of t. So this is just, we're going to differentiate like usual. So derivative of t squared is 2t. Derivative of t is plus 1. Same thing over here. We're going to calculate dy dt. So we're just differentiating with respect to time, and our function is in terms of time, so the variables match. So it's just our usual derivative, 3t squared minus 3. So there's some power rule there. All right, so let's fill this in. What is dy dt? That goes on top, 3t squared minus 3. What is dx dt? That goes on the bottom. That's 2t plus 1. And there we go. We have our derivative dy dx. So just note, dy dt, this formula is describing kind of the velocity in the y direction at time t. So this is measuring the change in our y coordinate as with respect to t, versus this derivative dy dx, this is measuring the change in our y coordinate with respect to x, with respect to the change in our x coordinate. So dy dt is measuring the change in y with respect to time. Dy dx is measuring the change in y with respect to our x coordinate. And so the way we want to think of this formula here, this function, is this is just giving us the slope of the tangent line at time t. So at any time we're interested in, plug it in, and we'll know the slope of our tangent line. Just like really, what do these parametric equations say? Well, this tells us our x position, our x coordinate at time t. And this equation tells us our y coordinate at time t. So with parametric curves and parametric equations, everything is kind of expressed in terms of t. So we have our x equation, which is telling us the x coordinate at time t. We have our y equation, which is telling us the y coordinate of time t. And we just calculated dy dx, our usual kind of slope of the tangent line derivative. And that's telling us, what is the slope of our tangent line at time t. And let's actually use that. Let's try example 2. We're going to find the equation of the tangent line at a specific point, 6, 2. So we have our x equation, t squared plus t. We have our y equation, t cubed minus 3t. Same equation as example 1. So we calculated the first derivative, and we got 3t squared minus 3 over 2t plus 1. So let's just write that down. And so we have these three equations now. And what we want to do is we need to figure out, okay, what time these equations are expressed in terms of t. We need to figure out what time do we actually go through this point. So that's what we need to do first. We need to find the t value. So we need to figure out, okay, we have our point. We know we're going to go through this point. What time do we actually go through it? And why do we need to know the t value? Well, we need to know the t value because that's how our derivative is expressed. It's expressed in terms of t. So in order to evaluate this, we need to know what time are we actually at this point. And the way we're going to do this is we have an x coordinate and we have an x equation. We have a y coordinate and we have a y equation. So we're going to set our x equation equal to 6. We're going to set our y equation equal to 2 and then solve those equations for t. And that will give us the potential time values here. So let's start with our x coordinate. And really you want to start with whichever one is going to be easier. So you look at these two equations. Highest power of t here is a squared. So if I'm going to work with this, it's going to be a quadratic equation. And I know I'll be able to solve that. Here I have a cubed. Might be able to do something, but it might be a little bit more difficult. So I'm going to start with the easier one. And so I'm going to take my x equation, and I know whatever time we're at, my x coordinate is going to be 6 because that's the x coordinate of our point. And then we just want to solve this equation for t. And that's what we're going to do. We're just going to go through the steps of solving for t. So in this case, we're starting with our x equation. And that's because it's a little bit easier than our y equation. So we take our x coordinate, set it equal to the x equation, and then we're going to solve this for t. All right, so how are we going to do this? Well, usually we want to try factoring. So let's get everything onto one side. And that should be a t squared plus t. Just wrote it down wrong. And then when we bring this 6 over, it's going to become a negative. So it'll be minus 6 equal to 0. Try factoring. This factor is very nice. So we get t plus 3 times t minus 2 is equal to 0. And so if we set each of these factors then equal to 0, it looks like we're going to have 2 potential times that we actually go through this point. So it looks like at time -3 we might go through this point, and it looks like at time 2 we might go through this point. So we know these two t values give us an x coordinate of 6. But in order for us to go through this point, not only does the x coordinate have to be 6, the y coordinate has to be 2. And so these are the only two possibilities for a time that we actually go through this point. So we can just plug these t values into our y equation and see what we get. So we're going to plug into y equation. So what do? Let's take -3 and let's plug that into our y equation. We're going to get y is equal to -3 cubed minus 3 times -3. And if we do the arithmetic here, this will be a -27 plus 9. We're going to end up with -18. And if we look at our y coordinate is 2, definitely not -18. So we're at a different point actually. So at time -3, we're actually at the point 6, -18. So we're not at the right point. Let's try the other t value. T equals 2. Plug that in. We're going to get y is equal to 2 cubed minus 3 times 2. 8 minus 6 is 2. And that checks out. So it looks like at time 2, this is the time that we're actually at this point. Both coordinates need to work out for us to be at this point. And at time 2, that looks like it's the only time that we are actually x is equal to 6 and y is equal to 2. All right, so we want to find the equation of our tangent line to the curve at this point. We actually know now the time that we actually go through this point. So what we want to do is we want to just evaluate potentially each of these to figure out our x-coordinate, our y-coordinate, and our derivative, our slope of our tangent line. So we're going to evaluate as needed. So if we take this time value, if we plugged it into here, that would just give us our x-coordinate. So we would get 4 plus 2 is 6. That's what we know already. Same thing if we were to take t equals 2, plug it in here. Well, we did that. We get 8 minus 6, which is 2. So we're actually given the x and y coordinates. So we don't actually need to go through and plug those in because we'll just kind of repeat that information. But if we say weren't given this point, we would need to take our t value and then plug in to find the x and y coordinates. So we're already given the x-coordinate and the y-coordinate for our point. But we do need to take this t value and plug it into the derivative to get the slope. So when we do that, we're going to take our derivative, 3t squared minus 3 divided by 2t plus 1, and we're going to evaluate this at t equals 2. Just going to use this big vertical line here, indicate evaluate. So we're just going to take our first derivative that we already calculated, and we're going to plug in this time value. So what do we get? Well, we get 3 times 4, which is 12 minus 3, which is 9. And then we get 2 times 2 is 4, plus 1 is 5. So we're just taking t equals 2. Wherever I see a t, changing it to a 2 and simplifying. So our slope is 9 over 5 here. All right, so for the equation of the tangent line, there's kind of 3 ingredients we need. We need the x-coordinate, we need the y-coordinate, and we need the slope. So let's actually put it all together. So what is our equation of a line? Y minus our y-coordinate is equal to the slope times x minus our x-coordinate. We found the slope is 9 over 5, and we were given our x-coordinate was 6, and our y-coordinate was 2. You might have to calculate these, but we were given these. Kind of the other side of that, though, is we had to figure out the time, which is actually a little bit harder. So, if you're actually given the time, just plugging in to get the x and y coordinates is not too bad. What did we have to do here? We were given the point, and we had to figure out the time where we actually went through that point. So there's a little bit more work here. If we were just given the time, you just plug in here, plug in here, plug in here, you'd have your 3 ingredients. We actually had to do this kind of preliminary work in order to find that time value. All right, so in any case, though, we ended up with our 3 ingredients that we need for our equation of a line. So now we're just going to plug in. So we get y minus 2 is equal to 9 over 5, our slope, times x minus 6. And there we go. We have our equation of the tangent line. And if we wanted to, we could solve for y here to get the, to get in the form y equals mx plus b. But I'll leave that up to you. So here we go with our equation of the tangent line. All right, so what we just did is here is a graph of our parametric curve. So this is parametric curve given by x equal to t squared plus t and y equal to t cubed minus 3t. So this is a graph of our parametric curve. And what we just did is we found the slope of our tangent line at the point 6, 2. And we found the actual equation of that tangent line. There we go. That's what we did. We have our so this is our tangent line at time t equals 2. Now you could there's a lot of other interesting points here. And you could try plotting a few different points on this curve just to kind of see where they are. But what you would see is that kind of the direction here. So we know with parametric curves, there's kind of a direction in how we go around this curve. So the direction is actually so think of this as like a particle that's moving in the xy plane. So it's kind of coming along and it's just tracing this out. So just think of it as like your pen tip as you're drawing this curve out. It's just describing the position in the xy plane. And we were investigating this point here, 6, 2, which we were at time 2. But there's a lot of other interesting points here. And you notice that with a parametric curve, you can kind of go through the same point twice, just at different times. So here, at this point, this is an interesting point. It looks like the point 2, negative 2. So we actually go through that point what looks to be twice. At 2 separate times. So if you're tracing this out, if we start down here, we go through that point once, and we keep going, particles moving around. We go through that point again. Now it's at a different time, and then it keeps going from there. So with parametric curves, we can go through that same point twice, and each time we go through that point, we're going to have a different slope of our tangent line, because when we first go through the point, we're kind of heading up. We're kind of heading in this direction. And then when we come back around for a second time, it almost looks like we might have a horizontal tangent line there, because our curve kind of flattens out temporarily. So it'd be good practice. Try to see if you can figure out what time we actually go through that point. You won't do it, but it's good practice. Find the t-value, or t-values, there should be 2 of them, where we actually go through this point. Another interesting thing to kind of see here is at this point here, if we were to look at our derivative, I kind of would have expected our derivative to be 0 there. And if we were to zoom in, let me get rid of that point for a second. If we were to zoom in, right around that point, it looks like it flattens out. So I would expect a horizontal tangent line there as well. does it mean when we have a horizontal tangent? Well, derivative dy dx is equal to 0. So another kind of fun thing to practice with is see if you can find the time value where we actually go through this point, 0, 2. Plug it in and plug that t value in and see if we get 0 for our derivative. It means we have a horizontal tangent line. All right. So these parametric curves are, we kind of get this really interesting behavior here that we normally wouldn't get with a just kind of a regular y equal to f of x type curve. All right. Well, for the practice, let's calculate the second derivative as well. So we have our first derivative. What was our first derivative? It was dy dx was 3t squared minus 3 over 2t plus 1. So we did that. Now let's calculate the second derivative. And we're doing the second derivative with respect to x. All right, so what do? Well, we're going to take our first derivative and we're going to differentiate it with respect to t. And then we're going to divide that result, whatever we get there, we're going to divide it by our x derivative with respect to t. All right, so let's work with what's on top here. There's a little bit more going on. So we have this expression in terms of time, and we want to do the derivative with respect to time. And what we see here is it's a fraction. We're dividing. So when we do this, we got to use quotient rule. All right, so let's go through this. How are we going to differentiate it? Well, quotient rule. So let's implement the quotient rule. So we write down our fraction as a product. So top times the bottom. Top times the bottom. Yeah, this is one way to remember the quotient rule. So we're just kind of writing this fraction as a product. Top term times the bottom, and then we do 2 copies of it. So top term times the bottom, and then in between we put a minus sign. And then in the first copy, we're going to differentiate the first term, and then in the second copy, we're going to differentiate the second term. So the kind of what's happening in the top here for our quotient rule, very similar to product rule. The only difference is we have this minus instead of a plus sign. So this is how we're kind of just implementing the quotient rule here. Derivative of the top times the bottom minus the top times the derivative of the bottom. All over our the original denominator here, which was 2t plus 1 squared. All right, so this is just the derivative of, with respect to t, of our first derivative. Then we're going to have all of this, so there's a lot of fractions going on. We're going to have all of this over dx dt. So let's simplify this down. Derivative of 3t squared minus 3 is 6t times 2t plus 1 minus 3t squared minus 3 times 2 all over 2t plus 1 squared, and then all over dx dt. And we could probably start filling in this dx dt, but we'll do it in the next step. So it's kind of a lot going on here with the top piece here, the numerator here. Multiply things out, so we're going to have a 6t times 2t, that's 12t squared. And then we're going to have a minus 6t squared. So 12t squared minus 6t squared will give us 6t squared. Then we have a 6t times 1, and then kind of no corresponding term over here. So we'll end up with a 6t. And then we have a double negative, so that'll become a positive 3 times 2, 6. and then this is all over 2t plus 1 squared. And then that's all over, what is our derivative with respect to x? Well, it's 2t plus 1. So when we simplify this down, looks like we're dividing by this 2t plus 1. We're dividing by 2 copies, and then we're dividing by a third copy. So we could simplify this into (6t squared plus 6t plus 6 over 2t plus 1 cubed). And so the way you want to think of this second derivative is it's the second derivative of y with respect to x. And so really we can kind of think of this formula. This is another formula to kind of add to our list. We have a formula that describes the x-coordinate. We have a formula that describes the y-coordinate of our parametric curve. We have a formula that describes the slope of the tangent line, dy dx. And now we have this other formula that really describes the concavity at time t. So this formula really describes the concavity of our curve at time t. All right, that's what the second derivative does. We can think of it that way. All right, so just a little practice using these, calculating these derivatives for parametric curves. All right, so next time we're going to see how to calculate the length of a parametric curve. So we'll look at the arc length for a system of parametric equations that describe a curve. So we'll see you then. Bye-bye.